Somewhere in Virginia, inside an Azure data center, a database schema update began to deploy. The change was routine, a normal part of Snowflake's continuous release process. The engineers who pushed it had no reason to suspect anything was wrong. By 3 a.m., queries started failing. Data analysts in Europe opened their laptops to start the workday and saw error messages instead of dashboards, SQL execution internal error, then another, then thousands. Within minutes, the same errors appeared in Oregon, then Ireland, then Mumbai, Singapore, Zurich, London, Sweden, Mexico, 10 of Snowflake's 23 global regions gone. And for the next 13 hours, one of the world's largest data platforms couldn't access its own data. This is the story of how a backwards incompatible database update brought modern data infrastructure to its knees, why rolling it back took half a day, and what it reveals about the hidden fragility in systems we trust to never fail. The invisible platform. Most people have never heard of Snowflake. But if you've ever looked at a business dashboard, analyzed customer data, or worked with any company that makes data-driven decisions, you've probably relied on it without knowing. Snowflake is a cloud data platform, essentially, a massive distributed database that companies use to store and analyze petabytes of information. Think of it as the warehouse where modern businesses keep every piece of data they own: customer transactions, website analytics, financial records, supply chain metrics, everything. Fortune 500 companies, startups, healthcare systems, financial institutions, they all query Snowflake millions of times per day. Data scientists write SQL queries, dashboards pull live metrics, machine learning models train on stored data sets, and until December 16, most of them assumed it would always work. The platform operates across 23 regions worldwide, distributed between AWS, Azure, and Google Cloud. Snowflake doesn't own the servers. It rents infrastructure from cloud providers and builds its data warehouse layer on top. This architecture is supposed to provide redundancy. If one region fails, workloads should fail over to another. But on December 16, redundancy didn't matter, because the failure wasn't physical, it was logical. And when your metadata schema breaks in a backwards incompatible way, every region that depends on it becomes vulnerable regardless of where the data physically resides. 2:55 UTC, the update. The incident began exactly as designed. Snowflake's release documentation describes a 3-stage deployment approach meant to catch problems before they spread. Updates roll out, gradually monitor activity, respond to issues, halt or roll back if needed. The system is supposed to complete follow-up within 24 to 48 hours. The December 16 update was a database schema change. Schema defines the structure of your data, what fields exist, what types they are, how tables relate to each other. When you query a database, the system checks the schema to understand what you're asking for. Snowflake's engineers made a change to this schema. The new version added or modified fields. Nothing unusual. These changes happen constantly in distributed systems. But this update was backwards incompatible. That means older versions of Snowflake's code couldn't understand the new schema. They expected certain fields to exist in certain formats, but the schema had changed those contracts. When the update deployed, previous release packages still running in production across multiple regions started querying the updated schema. They referenced fields that no longer matched, version mismatch errors, operations failed. Or they took an extended amount of time hanging indefinitely while trying to reconcile incompatible metadata. And because Snowflake's architecture relies on globally coordinated metadata services, the problem wasn't isolated to one region, it cascaded. Virginia went down, then Oregon, then Europe, then Asia. 10 regions simultaneously compromised. The first alerts at 2:55 UTC, Snowflake's monitoring systems detected the first anomalies. Customer queries were returning errors. Data ingestion pipelines, Snowpipe and Snowpipe streaming started failing. Data clustering, health checks reported degradation. Customers saw the same message everywhere: SQL execution, internal error. For data analysts just starting their workday in Europe, it was confusion. They refreshed, they reran queries, they checked their code. The error persisted. For automated systems, pulling live data every minute, it was silent failure. Dashboards froze at their last update. Business intelligence tools displayed stale numbers. Machine learning pipelines stopped ingesting new data. For companies operating on tight SLAs, it was panic. If your entire data infrastructure is in Snowflake and Snowflake is down, you have no failover. You're offline. At 4:30 UTC, an hour and 35 minutes after the first errors, Snowflake posted an update. We have identified the problem and are working on a fix. The problem: a backwards incompatible database schema update. The fix: rollback. But rollback isn't simple. Code can be rolled back quickly. State cannot. Why rollback took 13 hours? When Snowflake's engineers identified the root cause, the solution seemed obvious: revert to the previous schema version, push the old code, restore service. But schema changes don't work like code deployments. Once a database schema updates, it interacts with live workloads, background services, cached state, and thousands of running queries. You can't just undo it. Sanchit Virgogia, chief analyst at Greyhound Research, explained the problem. When a platform relies on globally coordinated metadata services, regional isolation is conditional, not absolute. By the time symptoms become obvious, rollback is no longer a simple option. Snowflake's metadata layer governs how services across all regions interpret data and coordinate behavior. When that layer changes in a backwards-incompatible way, reverting it requires careful sequencing and validation to avoid secondary corruption. Engineers had to halt the update propagation, identify which regions were affected and to what degree, assess the state of live data, what was corrupted, what was incomplete, revert the schema without breaking in-progress queries, validate that the rollback didn't introduce new version mismatches, monitor for cascading failures during recovery. The initial service restored by 14 UTC, then the estimate slipped 15 UTC, then 1630 UTC. Virginia Azure East US 2 took longer than expected. The region was stuck. Engineers worked through resolution steps, encountered unexpected issues, resolved those, and continued mitigation. Each update pushed the timeline back. Meanwhile, customers had no workaround. Snowflake's incident report was clear. There are currently no available workarounds for this issue. If you had replication enabled in non-impacted regions, you could fail over. But most customers don't. And even those who did had to manually initiate the switch. For 13 hours, data sat frozen, the human cost. If you're not a data analyst, 13 hours without access to a database might not sound catastrophic. But in 2025, data infrastructure isn't optional. Retailers couldn't update inventory metrics, e-commerce companies couldn't analyze customer behavior, financial firms couldn't run risk models, healthcare systems couldn't access patient analytics, logistics companies couldn't optimize routes. On Reddit, users vented frustration. I dealt with this yesterday. It took them way too long to roll back this change. One analyst described trying to meet a deadline with frozen dashboards. Everything just stopped. No queries, no ingestion, nothing. And we're paying thousands per month for uptime. For companies with SLAs tied to data availability, the outage meant breach penalties. For startups relying on real-time data pipelines, it meant missed opportunities. For analysts working on time-sensitive reports, it meant manual workarounds if any existed. And this wasn't Snowflake's first incident in December. Just days earlier, on December 10, the platform experienced degraded performance in one of its AWS regions. 2 outages in 1 week, 15:59 UTC resolution. At 3:59 p.m. UTC, 13 hours and 4 minutes after the first error, Snowflake posted the final update, resolved. Service had been restored region by region. Azure Virginia came back last. Engineers had validated the fix, monitored the environment, confirmed stability. Some customers would still experience delays in ingestion as backlogs cleared, but queries were running again. The preliminary root cause was listed. Our initial investigation has identified that our most recent release introduced a backwards-incompatible database schema update. Snowflake promised a detailed root cause analysis within 5 working days. As of this recording, that RCA has been published in Snowflake's community forums. The full technical breakdown is there for anyone who wants to see exactly what went wrong. But the technical details aren't the real story. The real story is what this incident reveals about modern infrastructure. The broader pattern? Snowflake's December 16 outage wasn't an isolated event. It's part of a pattern that defined 2025. Cloudflare crashed twice in 30 days from routine configuration changes. AWS USE AST1 suffered its 3rd major outage in 5 years. Microsoft's December security updates broke message queuing functionality across enterprise systems. Each incident followed the same script: routine change, unexpected failure, multi-hour recovery promises to improve. Gogia, the Greyhound research analyst, framed it this way: schema and metadata sit in the control plane layer that governs how services interpret state and coordinate behavior across geographies. Regional redundancy works when failure is physical or infrastructural. It does not work when failure is logical and shared. In other words, when the failure is in the logic layer, the schema, the configuration, the metadata, geographic distribution doesn't save you. Every region depends on the same contracts. When those contracts break, everything breaks. This is the hidden fragility of modern cloud platforms. They're not failing because of bad hardware or network outages. They're failing because of schema changes, configuration updates, and compatibility mismatches. And those failures are harder to prevent, harder to detect, and harder to fix. The security connection. Snowflake's December outage sits in a larger context. In mid-2024, approximately 165 Snowflake customers were targeted by criminals using stolen credentials from InfoStealer infections. Weak identity governance allowed attackers to access customer data. Gogia connected the dots. These are not separate incidents belonging to different risk silos. They are manifestations of the same underlying issue: control maturity under stress. In the security incidents, stolen credentials exploited weak identity governance. In the outage, a backwards-incompatible change exploited weak compatibility governance. The thread running through both incidents, inadequate safeguards under pressure. Snowflake's deployment process is supposed to catch backwards incompatible changes. Its three-stage rollout is designed to halt or roll back problematic releases within 24 to 48 hours. But on December 16, the update hit 10 regions simultaneously and took 13 hours to fix. The safeguards didn't work, or they worked too slowly, or they weren't designed for this failure mode. Either way, the result was the same: global data infrastructure down for half a day. The question that remains: at 15:59 UTC on December 16, Snowflake systems came back online, engineers restored service, customers resumed querying their data, the incident closed. But the deeper question remains unanswered. How do you prevent this? Snowflake's documentation already describes a staged rollout process: monitoring, validation, rollback procedures, and yet a backwards incompatible schema change still brought down 10 regions. CIOs can't rely on uptime percentages anymore. A platform can promise 99.9% availability and still suffer a 13-hour outage that destroys your quarterly metrics. The question isn't what's your uptime, it's how does your platform behave when assumptions fail? Because they will fail. Configuration changes will introduce incompatibilities. Schema updates will break version contracts. Deployment pipelines will miss critical issues. The fragility isn't a bug. It's a feature of distributed systems operating at scale. Complexity grows, dependencies multiply, and eventually something breaks in a way no one predicted. Snowflake will publish its root cause analysis, engineers will implement fixes, processes will improve, and then months or years from now, something else will fail in a new way. That's not cynicism, it's reality. The only question is, when the next blizzard hits, will we be ready?